As the vehicle is driving and handling the different curves in the road, handling characteristics from the driver input, and also accelerating and slowing down and stopping, that wheel and tire assembly is trying to act in multiple different directions in order to move the vehicle and manipulate the movement of the vehicle for where the driver wants the vehicle to go and how it's supposed to go there. So designed into the system are different components like stabilizer bars for one, and other things like links, control links. We know about control arms. I'll briefly review control arms here to talk about some of the other links. But the suspension system needs to be supported in multiple directions and not bind through its movement. So all these different links have to move with respect to each other and still provide stable, smooth operation of the vehicle. And it all comes down to keeping that tire in contact with the ground in order to have reliable, safe stopping and handling of the vehicle in any situation the driver may encounter. So today we're going to be looking at the different components and suspension systems that make this all possible on a vehicle across different suspension systems, different vehicle platforms, and different designs. Some vehicle designs are more specific to a certain type of driving condition, like a four-wheel drive or off-road application, possibly for handling purposes for a sport suspension, or maybe a comfort setting for a luxury car. Depending on the system is going to depend on what types of links and how complicated or how simplified the system might be. And usually when systems are more complicated, they are more susceptible to wear, as opposed to a more simplified design, which may not offer as much comfort for the driver, but the robust design of a more simplified system may lend itself to be more durable in a heavy duty or an off-road application. So we'll look at a few examples of that as well. Sway bars can go by multiple different names. Typically I refer to them as sway bars, and that's how a lot of manufacturers will refer to them. They can also be called stabilizer bars, anti-roll bars, anti-sway bars. All of them mean the same component. They're talking about a piece of spring steel, most often a piece of spring steel, that counteracts body roll movement. When the vehicle is rounding a corner or is on unstable ground and the body wants to tip one way or the other, the job of the sway bar is to resist that movement and keep the tires in more contact with the ground or optimal contact with the ground for better handling and vehicle stability purposes. If the sway bar is not present on a suspension system and the body is trying to lean during an off-camber situation, whether that's on a side hill or while the vehicle is making a turn, what that can do is that weight transfer to the outside of a turn is going to pick up weight from the inside wheels. And if that weight is picked up from those inside wheels, we're decreasing our contact patch between the tire and the ground and limiting the effectiveness of how we can steer, stop, and slow the vehicle down safely. Without those tires being held to the ground, we're decreasing our ability to stop and handle safely. I'm going to show you an example here of the forces that are typically acting on a sway bar. The end of the sway bar that curves outward from the long part that spans the width of the vehicle, on each end there's going to be a portion of it that sticks out, usually about 90 degrees to it. And the end is where the end link is going to connect it to either an axle or the suspension component that's moving, or to the chassis. So this part is supposed to be acting on the link, resisting the movement. That energy transfers through the spring steel to the opposite end, to the other side of the suspension, to help control the stability of the suspension as it tries to move. The mount bushings are going to mount the bar to the chassis or to the axle on either side. And through the movement of the suspension, as forces are acting on one side of the suspension or another, this bar is going to be able to twist. And that twisting motion is the characteristic of the spring steel, and it's going to transfer that energy to the opposite side. So it's using the vehicle's body sway or body roll to help apply more force to the side of the vehicle that is decreasing weight on the tires, increasing stability. Now as I pry down on the pry bar here, that end of the sway bar lifts up. That energy is transferring down through the length of the sway bar. So with the other end fastened and fastened to the bench top, and with the mounting it to the bench top as well, we have movement on one side, and the energy is transferring through the steel as it's twisting and acting as a force on the opposite end. Let's go back to the Jeep example. Right here is our sway bar mount bushing. On the opposite end is another bushing. So this is tied to the chassis across the main part of the bar. That bar, the bar turns and comes down to the end link. And this end link, so remember, the bar is fastened to the frame of the vehicle, to the chassis of the vehicle. The end link comes down to the spring plate that mounts the axle to the leaf spring. Sprung components refer to parts of the vehicle that are supported by the spring. So here's our spring, and it is connected to the axle. The axle is in contact with the tires and the ground and is considered unsprung weight. So the tires and the axle move with every irregularity in the ground. That energy goes into the spring, and the spring provides cushioning for the rest of the chassis. So anything above the spring is considered sprung weight. Anything below the spring or connected to the bottom of the spring, in this case it's the middle of the leaf spring, is going to be unsprung weight. So we have the sway bar mounted to the sprung chassis, the sprung weight of the chassis, and it is being connected to an unsprung component right here on the sway bar end link. So this is how it's connected. One advantage to this example on the Jeep is the fact that the sway bar can be disconnected at the links. Most sway bars are attached with hardware and are not easy to disconnect. In this situation, a sway bar may be disconnected to allow the axle more articulation and the suspension to flex more in an off-road situation, instead of the sway bar limiting how much movement there is in the suspension system and the body roll, but increasing that by removing the sway bar from being connected to the suspension. I'll show you an example of it. First, I'll show you the amount of body roll or sway with the sway bar connected. Now we will disconnect the front sway bar links and do the same example. Both sway bar end links on the front of the Jeep have been modified to be disconnected and reconnected for off-road and on-road performance. With the sway bar disconnected, our links are now separated, and we're no longer tying an unsprung component to a sprung component and offering stabilization of the vehicle. So this allows more movement of the suspension from the chassis to provide better articulation and flex in an off-road situation, and in that case, more flex is what gives you more traction. Depending on the design of the chassis of the vehicle and the manufacturer's design, the sway bars need to match the rest of the suspension system in terms of how much they're going to be able to deflect and articulate with the suspension. All sway bars should be able to move without resistance as the vehicle suspension compresses and rebounds. So as a vehicle hits a bump, the stabilizer bar or the sway bar is not under tension or load when both sides are doing the same thing. The time where these are active are when each side is trying to do something different, whether that's driving over uneven surfaces or whether it's going around a turn and trying to stabilize the vehicle. A couple of things that go into these can change the stiffness of the component itself. So these can be solid or they can be hollow. And just like on a regular spring, like a coil spring, the diameter of the bar itself is going to be one method of adjusting stiffness. A skinnier bar is going to have a lot more deflection in it. so it's not going to be as stiff. So a bar that is thicker or wider in diameter is going to be a stiffer sway bar. The other part is how far off from the bar the links are connected. The farther we come, the farther out we go from the bar itself, the more leverage we have to twist that bar. So a sway bar link connects at the end of the sway bar. If that, depending on how far away that is, determines also how stiff the sway bar is going to be. So not only do we have the thickness or the diameter of the bar determining stiffness, but also how far away the end link connects to it. A shorter distance is going to result in less leverage on the sway bar and will increase the stiffness of the sway bar. A longer attachment point from the pivoting part of the sway bar will result in a less stiff sway bar. Aftermarket sway bars and sway bar kits offer the adjustability of changing through multiple positions where that link is going to connect. So a person can tune their suspension to their preference, let's say in a race application, move it closer in to stiffen the sway bar, or move it farther out to soften the sway bar. Balancing the front and rear sway bars are what manufacturers have done when they were designing the suspension system. It's designed to fit that vehicle and the vehicle's purpose. Changing any of this is going against what the manufacturer designed into the system. Depending on what changes are made to a sway bar stiffness may affect things like understeer and oversteer, which understeer is where the front tires will turn, but the vehicle continues to push against those tires and not follow the direction that they're turned. And oversteer, which is what drifting is all about, is where the tires are turned and the rear tires lose traction. Sway bars have a lot to do with the handling characteristics of the vehicle and how it's going to react from the front to the rear. Typically, a soft front sway bar and a stiff rear sway bar will promote oversteer. On the example on the Jeep, where the end links have been modified, disconnect the sway bar for off-road and reconnect for on-road, newer vehicles have a feature built into the sway bar system. In between the two halves of the sway bar, there may be a separation with an electronic disconnect. There may be an electronic disconnect partway down the line, partway down the sway bar. Also, these can be hydraulically activated or electronically activated. On more complex suspension systems, and therefore more development money and costs going into the vehicle, which ends up being a more expensive vehicle to the consumer, the sway bar can actually be designed to increase or decrease its resistance to the suspension movement depending on a driver setting. So think about this example. On a vehicle that has different modes for the suspension, comfort, sport, normal, those may be three of the options that a driver may be able to choose from. Maybe they just have a sport button and they can click it on or off. What that can do on some vehicles that have, let's use the electronic example. The hydraulic example is not as common as the electronic. The same thing can be accomplished through hydraulic pressure from the power steering system, since there's about 1200 psi worth of pressure able to be utilized for function, whether it's for the hydro boost, the power steering, or in some cases, the active sway bar control. Electronic motors can do the same thing with less fluid lines, less potential for leaks, and overall less weight of the vehicle to simplify it a little bit more. So electronic motors are bridging that gap of where hydraulic functions used to be for some manufacturers. You still may see it. I'm not going to say they won't be developed anymore. I'm just saying that it's more common to see electronic active suspension components than it is to see hydraulic active suspension components. So I'm going to think about moving forward. But on the sway bar, if the sway bar is electronically controlled for active control stability, there is an electric motor that is going to allow more or less twisting to occur. The same way an electric motor can spin, the active sway bar control on an electronic stability control sway bar, instead of spinning a motor, it's going to use that same polarity, and one direction it's going to turn one way, and the other way it's going to reverse that polarity to turn the other way. Electric motors have 100% torque at 0 RPM. So this sway bar is actually operating at peak torque of the electric motor as the deflection is occurring. So if the driver sets a comfort setting, it's going to resist less and allow more movement, but it's still going to provide some resistance. If a driver selects sport suspension, then the electric motor can use more amperage to resist smaller amounts of movement with more force. So this is actually going to change the stiffness actively depending on driver input. And then you get into the really bougie systems that can take information from all different sensors, the G-force sensor, the lateral accelerometer, the wheel speed sensors, the pitch and yaw rate, steering angle position, the torque on the steering column. All these things can be put together and interpreted by a module that can send an output command to the active control sway bar, with all these systems giving inputs, and that control module outputting a signal or a command to the electronic motor on the active control sway bar that can actively adjust stiffness while the vehicle is driving through different scenarios without the driver input. It's doing it automatically through the function of the other sensors in the system. The example on the Jeep: manually disconnect, tie the sway bar up to the chassis so nothing is hitting or binding, and it allows more movement of the chassis. On newer Jeeps or newer off-road vehicles, they may have an automatic disengage and engage switch that the driver can disengage the sway bar without even getting out of the vehicle. This is often going to be an option that is on a higher end off-road capable vehicle. So maybe not all Jeep Wranglers have it, but probably the Jeep Wrangler Rubicon or some of the more advanced trim levels of Jeeps, to add that extra bit of luxury to somebody who owns the vehicle, or convenience for somebody who owns the vehicle. Typically, certain criteria need to be met in order for the vehicle to disengage the sway bar. Again, it could be a safety hazard, so it's not going to allow the driver to disengage the sway bar while they're going through S-curves or going down the highway at 50 miles an hour. Typically, it's going to be done under 4 miles an hour, and the vehicle may have to be on a level surface. If the vehicle's on an off-camber road surface, that may put stress on the sway bar and it may bind when it's trying to disconnect. But if all conditions are met and the driver selects to disengage the sway bar, the electronic function of the sway bar can disengage, and then it's free to spin one half against the other without any resistance. So without disconnecting the end links, the disconnect happens in the electronic portion of that sway bar. When we're talking about control arms with ball joints, there were some control arms that had 3 points of contact, 2 at the chassis and 1 at the ball joint. The ones at the chassis are designed to allow pivoting across the bushings, torque with vehicle weight, and allow that suspension component to travel up and down. Now, as the vehicle is accelerating or slowing down with torque forces through the drive wheels and braking forces, all that transfer is going from the tire to the road, and the road is acting back on the tire itself. So this component has 2 points of contact at the chassis. So that's going to resist the control arm trying to pivot backwards or pivot forwards. So this is a rigid component and does not need any additional links to stabilize it on the chassis in order to help guide that wheel where it's supposed to go. Other suspension systems have a lower control arm, like this example, where we have our pivoting ball joint out at the end. We have a point where our strut will likely connect to right here. This would be probably where a sway bar would connect to, and then our pivoting point on the chassis. So this is going to perform the same movement as the other control arm. So both control arms are going to have this movement to them in the suspension system. The difference being that this one is inherently unstable because there's nothing resisting the fore and aft movement of the control link, of the control arm. So we need something here to provide that contact with the chassis in order to stabilize this lower control arm. This is one design of a strut rod. A strut rod can go by a couple different names as well. Radius rod, compression rod, tension rod. Those different names of this component will make a little more sense as we continue. In order for this component to resist the forces acting from the tire back to the control arm, it needs to be controlled fore and aft. So we're not supposed to be getting this movement out of this control arm, because then our wheel and tire would be moving back and forth in the fender and hitting other components. Not going to be safe, not going to be practical. So what these usually do is, through mounting holes or mounting studs, will connect to the control arm. And then the other end will connect to the chassis. So this component here, through these bushings, will sandwich around a chassis bracket, and it's going to allow some movement up and down through the deflection of the bushings. It's going to allow some movement up and down. So that's not going to bind the movement of the control arm as it moves with the suspension. What it's also going to do is provide that third point of contact, that triangulation. As it's connected to the component, it's going to resist fore and aft movement of the component because it is mounted into the chassis. So it is a radius rod because it moves from one end to the other end with the suspension travel on a radius. It's called a compression rod because as that, let's say this is the front of the vehicle right here, as that fore movement, that forward force is acting on the control arm, this is being put under compression. So this bar is resisting that compression. So compression rod. Also, this bar is going to resist tension by doing the same thing in the opposite direction. So it is providing that fore and aft stability of the lower control arm if that lower control arm is only connected to the chassis at one location. This provides that triangulation, that strong geometric triangular shape that will stabilize the wheel on the suspension. This is an example of another tension rod or compression rod, strut rod. And they can be designed slightly different ways. Here's the one from our example. There may be a bushing of this type on one end that connects to the suspension, and it may connect to the chassis in different ways as well. This is a popular way of mounting it to the chassis, where these two bushings would sandwich in between the bracket that mounts it to the chassis of the vehicle and provides that radius function of it. So strut rods are there to resist fore and aft movement and stabilize the lower control arm, where we would otherwise have a triangular shape control arm providing its own stability. So depending on what the manufacturer decided to do with the suspension configuration on the vehicle, it may be designed with a lower control arm like this that has 2 points of contact on the chassis and one at the suspension, or have 1 point of contact at the chassis, 1 point of contact at the suspension, and then need an additional link to it in the way of a strut rod, compression rod, tension rod, radius rod to resist fore and aft movement. Let's tie some of this stuff together. So in this suspension example, we are using coil springs. Coil springs are inherently unstable. They require different control links in order to stabilize the components that they attach to, because they only offer stability in one direction, from end to end. That's the only way that a coil spring is supporting suspension. It does not control lateral movement or fore and aft movement. We need control links in place in order to use coil springs. The minimum is 3. This would be considered a 3-link suspension. If you have 4 links, 4-link suspension, 5-link suspension. So on this vehicle, we have the axle and the tires, And this piece represents the chassis of the vehicle. This is the simplified of the simplified. The vehicle is going to be subjected to lateral forces, whether that's due to gravity and traversing a side hill or an off-camber road situation. As the vehicle is handling across lateral forces, the axle is connected to the ground through the traction of the tires. Those forces going one way or the other are going to that energy is going to transfer through the springs themselves. Now, without any control links, the chassis is not going to be stable on the coil springs. So the popular method for controlling the movement side to side of the axle, so for example, when looking at vehicle specifications, there's a couple dimensions that are mentioned through the manufacturer's engineering points. One of them is track width. Track width is the distance from one hub flange to the center of another hub flange across the width of the vehicle. The wheelbase is from the center of the axle from the rear to the center of the axle in the front. Track width is side to side. So the bar or the link that is going to connect the chassis to the axle and stabilize is called a track bar. There will be a bracket on one side of the chassis and a bracket on the opposite side of the axle, and that link or that track bar can now pivot. This can pivot and allow movement of the axle up and down. So it's not going to bind the suspension, and because this is a rigid bar, it's not going to allow any lateral movement side to side. One of the drawbacks to this is as the suspension moves throughout its suspension travel, you can see it operates on an arc because this is a radius. We have a pivoting point here and a pivoting point here with a rigid bar in between. So as the suspension goes up and down, this bar is going to travel on an arc. Modified suspension systems, like on an off-road vehicle, are subject to this not being designed properly and allowing too much of that arc movement. What this arc movement translates to is a little bit of side-to-side motion as the axle goes through the travel of the suspension. The distance between this bracket and this bracket may be shorter or longer because this is operating on a radius, and it's going to allow a little bit of side deflection. This isn't as critical in an off-road situation as it is maybe in a road track or a sport handling suspension system, where a dip may be encountered during a turn, and during that dip in the turn, the axle may have a slight twitch to the side during that compression of the suspension system. Now, in a high-performance application, that little bit of nominal movement can be a very adverse handling characteristic of a vehicle going around a track. There's another variation of the track bar that allows for complete tracking of the axle, and that's called a Watts link. This example is a little challenging to illustrate on a whiteboard, especially with my advanced artistic abilities, but I'll briefly cover it, and I'll bring it up more in person, because this is a very well-designed system for limiting how much movement the axle moves side to side on a coil spring suspension. The Watts link is a variation of the track bar. Instead of having one bar that spans from the chassis on one end to the axle on the other end, it's broken up by a pivoting link in the center. So this pivoting link will move on its center pivot point, and that's typically mounted to the differential on a solid axle. Then it is then connected to the chassis from one end of the link to the axle, and from the opposite end of the link to the chassis. As the suspension compresses and rebounds, these links, these bars, are going to move on a radius just like a track bar. But that radial movement, that angular movement, is going to be equalized by this link. So as this arm pivots downward and tries to move farther away from its mounting point, this link is going to pivot. It's going to allow those links to move on their respective arcs and have a piece in the middle that pivots with the suspension movement. The main advantage to this, the big advantage to this, is that you have true up and down motion with the zero lateral movement. The upper link and the lower link radius are both compensated for through the Watts link pivot in the center. So this is still connected rigid from one side of the chassis to the opposite side of the axle through the links, and that allows the suspension to travel up and down with zero lateral movement side to side. This is more of a handling characteristic suspension for a high performance vehicle or for a luxury vehicle with a solid axle, as opposed to a track bar setup on an off-road situation. You get less articulation and suspension movement out of this suspension with the amount of links and the brackets and the clearances. It's going to offer less articulation of the axle in relation to the chassis, but is a great way to design a suspension system for a road and high performance or track use. Let's look at a side view of a coil spring suspension. The track bar or a Watts link can locate the axle from moving left and right under lateral forces of the suspension system. What about fore and aft? In a coil spring suspension system, we need at least 3 links of contact in order to provide stability for the axle or to provide stability for the suspension. Some other links in a suspension may be called control arms or radius arms. Radius always implies that they pivot on one end and swing on the opposite end. Solid axle coil spring suspension is very basic and is easy to illustrate some of these concepts. There will definitely be more complex variations of this type of suspension setup and with the links that are involved, but I'll give you an example of some of this just on a solid axle like the Jeep if it were not leaf spring but coil spring, and then I can show you an example on a Jeep that I have access to that does have this type of suspension. This drive wheel wants to rotate. As power is given from the engine through the transmission, comes into the axle, and if the tire wants to propel the vehicle forward, the equal and opposite reaction of that is the axle wants to spin the opposite direction. So with these forces, rather than the forces acting just from the brakes, but when we have torque forces being supplied to the tire to propel the vehicle forward, the axle on the vehicle wants to go in the opposite direction. A coil spring is not going to stabilize that. The coil spring needs some help. And through the addition of some links, that's very possible. This right here is our axle housing. Off of that housing, we're going to have a bracket coming up and a bracket coming down. Connected to the upper one, we're going to have a radius arm coming up here, and off of the lower one, we're going to have a radius rod coming up to here. This is a typical configuration of a 4-link suspension, where we have a control arm, where we have control arms or radius arms on 2 sides of the vehicle, upper and lower. The upper ones are typically going to be a short radius rod, and the lower one will be a long radius rod. And the difference in length is going to change how much they change angle down at the axle and provide optimum driveline pinion angle. So with the track bar, keeping the axle from moving side to side, our radius arms or our control arms, these can be considered a trailing arm, a control arm, or a radius arm. These links are going to provide support to the axle. So under torque forces, as the tire tries to propel the vehicle forward, the axle wants to pitch the opposite direction. These links are going to prevent that from happening. These links are also going to keep the axle from moving forward and rearward, or fore and aft. And the track bar, or the Watts link, is going to keep that axle tracking with the vehicle chassis. So that side-to-side lateral movement is going to be handled, the fore and aft movement is going to be handled, the torque forces are going to be handled. So this is a typical link type suspension for coil spring suspension on a solid axle vehicle. So I'm stretching my abilities here, trying to convey another example of suspension system. So on our previous illustration, we were looking at the upper and lower control arms of a vehicle, and with the use of a track bar to keep the axle centered on the chassis and moving, keep it from moving laterally side to side. If you want to go down the rabbit hole of independent suspensions, this is more of an off-road style suspension, or on a vehicle that may be lowered with airbags is typically where I've seen this as well. But this is what's referred to as a double triangulated suspension system. It's a 4-link, so we have 1, 2, 3, 4 links. Due to the angles and the triangulation of the links in the system, the upper control arms in orange and the lower control arms in green are opposing angles on a triangulation plane. And what this is doing is allowing the suspension to flex to optimum articulation without having any binding components like a track bar limiting the suspension from being free to flex. So with these double triangulated links, this system does not need a track bar because the triangular design of it on 2 planes helps locate that axle through the suspension travel of the upper and lower control arm. Like I said, you can go down the rabbit hole. Another one may have a singular connection on the differential or a bracket above the differential, but this is an example of a coil spring or airbag rear suspension that uses control links in order to stabilize and position the rear axle without the need of a track bar. It takes a lot more engineering and figuring out the geometry so things don't bind during the suspension travel, and if things are binding, that will lead to premature wear, limit of the suspension travel, performance of the suspension, and possibly wear and breakage. For this example, we'll be looking at a 2000 Jeep Wrangler that's had some modifications done to the suspension system for off-road use. Here you can see the lower control arm spanning from the chassis back to the lower part of the axle. This vehicle is using coil springs for the suspension. This is the lower control arm, and up here is the upper control arm. The upper control arm is considerably shorter than the lower control arm. It may not be easy to see in this example, but there's a bracket on the back of the axle, and this rod here is our track bar, and that's keeping the rear axle centered with the chassis. Due to the space constraints in here, it's hard to get a good view with the fuel tank in the way. But this is looking at the rear side of the axle on the bracket, and since this Jeep has a suspension lift on it, there's an extension bracket for the track bar to limit how much that arc travel affects the movement of the axle. And you can see the track bar spanning the distance from the axle up to the chassis. And here's a track bar on the chassis end connected to the frame, and then that goes down to the axle. Depending on the manufacturer's market for a certain type of vehicle is going to determine how much research, development, and overall cost and money they put into developing a vehicle and building it. This will be the determining factor when it comes to things like active stability control on a sway bar versus a permanently fixed sway bar that doesn't disconnect, it's not adjustable, it's there, it's engineered to meet the specifications for the system, and it keeps it simple. So it's easy to get off in the weeds when we're covering these different systems and you see a vehicle with an elaborate system that's more complicated than a vehicle that has a simpler system. What I'm hoping to do is provide you with some examples of some of the more simplified systems to where you can get those concepts kind of get those concepts down and then be able to determine how different manufacturers do different things as they make more or less complicated suspension systems. Keep in mind the basic function of the suspension system is to keep the vehicle isolated from the irregularities on the road surface, keep the tire in contact with the ground, provide comfort and safe handling of the vehicle for the driver and the passengers, and also to not bind in the suspension movement. So when we have multiple links moving with respect to each other, they have to be designed to a point where they don't bind and limit the movement of another link that's operating in the same system. Bindage leads to premature wear, failure of components, possible breakage of components, and ultimately unsafe handling of the vehicle. If there is a link that is bent or damaged, it may be offering more movement than it's supposed to. It may be changing the arc on its radius, which may cause bindage in other areas. And it may come out as uneven tire wear, or it can come out as an unsafe handling characteristic of the vehicle. It's best to understand these concepts on a more simplified scale and build upon that knowledge for the more complex systems. I hope I was able to get some good information for you to glean from on this topic. And until the next one, thank you.